got it.
Yeah, there's one.
Yeah, we can, once we're done with lecture, we can spend the rest of class going over whatever you guys want to go over. You guys always have the rest of class to do whatever you want. Alright, so we've already briefly stepped into chapter 8 last time. Chapter 8 is all about parallel lines, and I told you we're going to introduce our last postulate in this chapter. But our first definition. Definition 8.1, what does it mean for two lines to be parallel?
It's not really never intersect. It's that, the distance between.
Line L is parallel to line M if and only if what?
The distance between them never changes.
No, that's not our definition. That turns out to be the case for parallel lines in Euclidean geometry.
They will never intersect.
They don't intersect.
That is the definition. Okay,
Yeah.
I can't remember if it was that
Two
one.
lines are parallel if and only if they never intersect. Okay?
Yes.
So that's the definition. Now, we talked a lot last time about lines, for example, in a hyperbolic geometry. Two lines that never intersect, but the distance between them grows. Right? We were thinking about those as the lines on the saddle. So you do not have to preserve distances to have parallel lines. And it's...
But wait.
One of the ways, we talked a little bit about Euclid's fifth postulate.
Oh, that's right. We talked about how. Yeah.
And this is one of the ways that people went to do it. Because a lot of people were convinced that Euclid's fifth postulate should somehow be able to be proved from his other four. And there was a huge effort throughout history to try and prove it from his other four postulates. And one of the ways someone came at this is he says, well, if lines are parallel, the distances have to be the same between them. And then he used that to prove Euclid's parallel postulate. But it turns out saying that the distance between two lines has to be constant is logically equivalent to saying, given a line and a point on the line, there exists a unique line to a given point such that the two lines never intersect.
Right.
So rather than
because the line goes
proving
from
a
that
postulate,
way to that way.
they
It's slightly
introduced a
on
new postulate to try and prove the postulate.
Right.
And so it turns out it's just logically equivalent. And you can use either of those postulates that you want. You're in the same geometry.
Yeah, but technically, I mean, actually, I don't know that.
Alright, so that's our first definition. We know what a parallel line is. Now let's prove that parallel lines actually exist. Now I told you up till now, we are either in Euclidean or hyperbolic geometry. We have not separated the two fields yet. Everything that we've proven so far works in both. So right now we could be on a flat board or we could be on this infinite saddle. It's only the last postulate that we introduced that finally says, okay, we're for sure in the whiteboard and not on a saddle. So first we're going to prove that there are parallel lines.
Okay.
And then we'll introduce the last postulate. So there are parallel lines in both these geometries. So, theorem 8-1, if L is a line and A is any point on L, then there exists at least one line through A parallel to L. So we're doing theorem 8.1. Theorem 8.1, and it says, if A is any point not on L, comma, then there exists a line M through A such that M is parallel to L. Okay. So, draw a picture to the side here. What are we trying to prove? We're trying to prove that if we've got our line L here, and I've got a point A not on L, then there exists some line through A, we're going to call it line M, such that the two lines are parallel.
Right.
Okay, so here's how we're going to do this proof. So first thing I'm going to do is I'm going to put some random line, call L prime, through A,
That is not parallel.
and it intersects some point over here, we're going to call it B.
Okay.
So some line, call it L prime, I guess,
Intersects B. Intersects
and
L.
it intersects L at B. So, 1. Let L prime be through A and some point on L, call it B. Okay, so we've got this line L prime. goes through A, goes through B. Now, what am I going to do at L prime? I am going to now pick a ray. I may construct a ray.
That has the same angle as ABL, or the line, the angle between L. I don't know how to say that.
Yeah, we'll just call this one angle B. You got the right idea. So I may construct a ray R.
One.
Maybe we'll just call R. I don't think we'll need more rays.
We-
So we'll construct an R angle. We'll construct a ray here, so that angle A is congruent to angle B.
Okay, right.
All right,
And you can do it the other way too.
and I can do it the other way too.
Yeah, you can do it.
Yeah, it doesn't matter if we think about angle B over here and R going that way, and we're talking about those angles.
Same thing. Why you don't have to call it A, B, C, or whatever.
Yes. So let R be a ray from A such that angle A is congruent to angle B. Now, how do I know that such a ray exists? That goes all the way back to our existence postulates for the congruence of angles. Given one angle, there exists some ray such that we get another congruent angle from that point.
Right.
Okay. Can't remember the postulate we're using there. But now we have these two angles. Okay. And I guess I'll call,
This you can call that line N.
yeah, 3. Let M be the line through R, just like we have it labeled M rather than R. Okay, now let's think about this. So here's line M. We're trying to prove that these two lines are parallel, right? I'm trying to show that M is parallel to L. Maybe put their labels over there. So I want M and L to be parallel,
Right.
which means what?
Go intersect.
They don't intersect. So I'm going to assume by way of contradiction that these two lines intersect. So I'm going to assume by way of contradiction that our picture, if we go out far enough, we get a picture like this, and the two lines intersect at some point C.
Right. But that's impossible because B and A are the same angle. And if they intersect, then they're not the same angle.
So that's impossible because angle A and angle B are the same angle.
Right. And if
Why is that impossible? Why can't this angle be the same big as this angle?
Because they're not,
because if they intersect, they're like this, and this angle is now different than this angle.
You're using a lot of hand-waving argument there.
they're
You
not
got this.
growing at
Okay,
the same
Exactly
pace.
what we talked about earlier today.
Angle B is the same
Why can't this angle be as big as this angle?
as big.
Yeah, why can't this be the same size as this?
It is.
Notice that ABC makes a triangle,
Okay.
right?
Yeah.
Right.
So ABC makes a triangle, and that angle is the same big as that angle. Why is that impossible?
It can't be because of the opposite.
It's an exterior angle.
Right.
Oh.
This would be an exterior angle to triangle ABC.
No, it wouldn't.
This angle would.
No, it wouldn't.
Yeah.
The other one would.
No,
This,
Kendrick.
That would
our
be
triangle
the-
is right here, right here, right here, right here.
Okay.
Right.
If that was a
So
triangle,
this is our exterior angle to the triangle.
the angle
It's
A
outside
in
the
the triangle would be underneath.
I know that. I don't think that's where the exterior angle is.
Yeah, if you got some triangle,
Right.
here's the exterior angle.
Is that what it looks like?
Yeah. Here's a straight angle. Here's our triangle. Let me draw a picture closer to what this looks like. Your triangle could also look like this. This is still an exterior angle.
Yeah, that's true. Yeah.
Okay, so this is an exterior angle. This is a triangle. ABC is a triangle. And you have an exterior angle congruent to
Right.
one of its opposite interiors,
Just because it's 7-1, we
which
know.
is impossible.
Right.
Perfect. So for assume by way of contradiction that M intersects L at C, at some point C. So you've got ABC.
Oh, this is a big triangle.
Then angle A is an exterior angle. And angle A is congruent to angle B. Contradiction. 6. Therefore, M is parallel to L. Okay, kind of cheated a little bit in my proof here because we assumed C was over here.
Right.
These two lines could have intersected over here. All that would have changed is we call this angle A and this angle B, and it's the same
Wait,
thing.
why did you say angle A and angle B are congruent?
They are.
By construction, let R be a ray from A such that angle A is congruent to angle B.
Okay.
So we construct, remember what our picture was when we started. We started out with A and not on L. And so we started by constructing a line through A and then making an angle so that this is the same thing as that. All right, any other questions on that proof? Good? Okay, so what did we prove so far? We proved that if you have a line and a point not on the line, then there exists a parallel line through the given point. So we proved that there's at least one parallel line through the given point. Can there be more than one?
Yes.
Yes? No?
No.
What's
Through
the
same-
answer?
Through the same point?
Yes.
No.
If I have a line and I
Yeah,
have a
sure, that
point
can
not
be-
on the line,
it's
how
the
many
same
lines
line.
can I draw through that point parallel to this line?
One.
Oh, one.
In our geometry, it turns out it's going to be 1. If we were in hyperbolic geometry, it turns out that there's infinite. So far, we proved that there's exactly 1. Now, here's where we finally split. And we're in our geometry, and we're not in hyperbolic geometry. So our final postulate is that if you have a line and a point not on the line, there's no more than one line through the given point parallel to the given line. We already proved that there's at least one line. The postulate is, and there isn't more than one line.
Okay.
So that's our last postulate for our geometry.
That's all.
That's it.
Really?
That's our last postulate for planar geometry. So we'll continue with proofs. We still haven't done a lot of cool things, like obviously the Pythagorean Theorem is a famous one, but the Pythagorean Theorem only holds in
This geometry.
this geometry. Why are you shaking your head at the Pythagorean Theorem?
I don't know. I like it.
You don't like the Pythagorean Theorem?
It's probably out of the top, so it's a good way.
Oh my goodness. You like the Pythagorean Theorem, you just don't know it.
How can you like it if you don't know what it is?
How can you not like it if you don't know what it is?
Because the
Were you to know what it were,
what we
you
see
would like
is
it.
bad.
Because let me tell you what it says. Because it's amazing what it says. Kind of skip ahead here. What does the Pythagorean Theorem say? It says, imagine I have this right triangle.
Okay.
And what I do is I construct over here a square using this side. And I construct over here a square using this side.
Interesting.
And then I construct over here a square using this side. You have to forgive my drawing.
Why? This is fun.
The area of this square plus the area of this square is exactly the area of that square. Every time. Doesn't matter the triangle you use.
That is so cool.
As long as it's a right triangle,
That is so cool.
then that is always and forever the case.
Wait, but what do you get your length from the top one? Oh, it's a perfect square. Right.
So this is congruent to that, it's congruent to that, it's congruent to that. That's congruent to that, it's congruent to that, it's congruent to that. That is congruent to that, it's congruent to that, it's congruent to that, and then they're all right angles.
Actually, it's really cool.
Pick a right triangle. Construct these three squares. The area of that square plus the area of that square is exactly the area of that square. Perfect. No margin of error. Every time. Doesn't matter the right triangle you choose.
And is half of that, half of the area of that square, the area of the
When do
triangle?
we get into lengths? and stuff?
Now, so if one way we could say that is imagine that this side had length little a. Then the area of this square would be little a times little a, or little a squared. And if this side had length b,
A squared plus b squared equals c squared.
then this would be little b squared. And if this had length c, then the area of this square would be c squared. That's what we mean by a squared plus b squared equals c squared. If a and b are the lengths of the legs of a right triangle, and c is the length of the hypotenuse, then a squared plus b squared equals c squared.
That is so cool. That actually is really cool.
So it's a very amazing theorem. It's a very surprising theorem. There's nothing intuitive about that. And the fact that that perfectly holds every time, it's
I
phenomenal.
think we've just been taught it.
Right, you were told, here's a formula, memorize it, here's where you use it.
Right.
Correct.
Which is terrible.
Right. I've never seen that before, ever.
And
It's so cool.
since we're on it, maybe we'll take a quick detour. Because it's cool proof to see this. We'll come back and do it a different way here. Well, I'm not sure how we're going to do it with this book yet. But I'll give you the standard picture way of seeing it. So a way that you can see it clear to your eyes, super intuitive. Actually, we'll come back to it at the end of this chapter. Because first I need to use the fact that the angle sum of any triangle is 180 degrees. Or is a straight angle. Which we'll prove here.
Right, that was on the test.
So.
That was on the midterm. And we had
Oh, it was?
Yeah.
Oops. We haven't covered that yet.
Wait, what was?
Sorry about that.
The thing of the
Okay,
the same
let's get a bunch of definitions.
Which I just went and looked and found it in the book.
What problem?
I can't remember. 14.
Don't worry about it. Okay. So a bunch of terminology.
Yeah, 14.
If I have two lines,
Oh, was that construction? 14 construction. That's the
we'll worry about later. Alright, if I have two lines and a line that intersects both those lines, the line that intersects both of them we call a transversal. Now, I'm going to label a bunch of angles here. Try and label it the same way the author does. Angle 1, angle 2, angle 3, angle 4, angle 5, 6, 7, 8. Okay, label all those angles. We call 3, 4, 6, and 5 the interior angles. We call 2, 1, 7, and 8 the exterior angles. We call 8 and 5 alternate exterior, or 8 and 2 alternate exterior angles, 7 and 1 alternate exterior angles, 3 and 5 alternate interior angles, 6 and 4 alternate interior angles.
For what?
They're just names
Interior.
when you have a picture like this.
Yeah.
They're just names when you have pictures like this.
I remember that.
So you'll get used to talking about alternate interior angles and alternate exterior angles, especially when dealing with parallel lines.
And then 2, 3, 6, and 7 are exterior, right?
1, 2, 7, and 8 are exterior. So these lines go on like this forever. The ones in here are interior, the ones out here are exterior.
Oh, okay.
Okay. Alright, so just terminology. We didn't talk about two rays pointing in the same direction. What's the definition for that? What does it mean for if I have two arrows pointing in the same direction? Is this ray
They're the same.
and this ray pointing in the same direction?
No.
No. Is this ray and this ray pointing in the same direction?
No.
No.
Yeah, kind of. Perfectly?
Perfectly.
Oh, then it means.
Are this ray and this ray pointing in the same direction?
Yes.
Plausibly from our picture.
Right.
Okay, so what does it mean for two rays to be pointing in the same direction? By definition, here's what it means.
They're parallel.
It means, well, almost. It means, first off, draw a line through both their endpoints. One, the rays have to both be on the same side of the line.
And two.
And
angle
two,
A's
the lines
and
sort of have to
B.
be parallel.
Right, which
So
means.
what has to be parallel?
The lines.
The rays basically have to be parallel. The lines through the rays have to be
L1
parallel.
and
Same
L2.
thing as the rays being parallel. So that ray is parallel to that ray. And they're on the same side of the line that you draw through their endpoints. That's what it means for two rays to be pointing in the same direction.
So does 5 and 7 have a name for it?
5 and 7, you already know the name of those angles.
They're opposite. They're vertical angles, right?
They're vertical angles. Yeah, that's what we call them.
So 8 and 2.
All right. So let's see. We proved that. We proved that. 8, 3. Oh, that's just labeling all those. Okay, so our next theorem. Let L1 and L2 be cut by line L. If L1 is parallel to L2, then the interior angles are congruent to each other and conversely. Okay, so our next theorem here is going to be theorem, this is 8.4 now, because we did a few definitions. So theorem 8.4. Let L cut L1 and L2. Or in other words, L is a line that intersects the lines L1 and L2.
Why don't you just say intersect? What's the difference between intersect and cut?
It's just a way of saying it intersects both of them in a fast way.
Okay.
Rather than saying it intersects this and it intersects this. We say it cuts these. Just means it intersects both of them.
L1 cut L cut L1 and L2.
Then L1 is parallel to L2 if and only if I think here we're going to use alternate interior angles. if their alternate interior angles are congruent to each other. If and only if they're alternate.
Oh, it's alternate, not opposite?
Yeah, alternate interior angles are congruent. Okay. Make sure I have everything right. Okay, we got it right. So let's draw out our picture and see what we're doing here. So I've got a line L1. I've got a line L2. Let's see, which way do we want to go first? Let's first go this direction. So first, let's prove it this way. Notice that this is an if and only if proof. So I need to show that if L1's parallel to L2, then their alternate interior angles are congruent. And then I need to show the converse. So let's go this direction first. So assume
Oh, yeah, and then a problem like this.
L1 is parallel to L2.
And then a problem like this was on the test too. I think.
Alright, so here's our picture. I know L1 is parallel to L2, and here's L, cutting both of them, right?
Yes.
I know that this is parallel to this. What am I trying to do? I'm trying to prove that alternate interior angles are congruent.
Right, which we proved.
Which means I'm trying to show that this angle and this angle are congruent.
Right, which is, which we know because we know that angle A, which is where it was before, is congruent to angle B, right?
So you're thinking about this, we're calling that A, we're doing B, you're thinking about calling this angle A, right?
Yeah, so that A is congruent to angle B, and we know that vertical angles are congruent. So thus, the vertical angle of angle A, which is the opposite angle of A, angle B, is congruent. It's congruent.
Okay, I think you got the right idea. So we have this line is parallel to this line.
Right.
So you're saying the crux of the proof is arguing that this angle is congruent to this angle.
And we know that that angle is congruent to it.
Right, so how am I going to argue that this angle is congruent to this angle?
We just already proved it in A1.
Almost. We proved that if this angle is congruent to this angle, then the lines are parallel.
Okay, so we assume that they're parallel, and that means.
Now we got to go the other direction.
Right.
So, assume L1 is parallel to L2, comma, and let A, B be the points where L cuts L1 and L2. Okay, so we got that labeled, got our picture labeled like this so far. Now, here's what I'm going to do. I'm going to pick some point up here, call it C. I'm going to pick a point. How am I going to label these? I kind of need to label a point up here, C, so we can talk about angles. So I'm going to call that point C. To let C on L such that we have CAB. Okay, so just labeling that point C. But here's what I'm going to do. Now I'm going to pick a point over here, call it D, such that this angle is congruent to this angle. And I'm going to argue that D must lie on L1.
Okay.
That's going to be the crux of this. So let's see on L1 such that. And let D in the interior Well, it's not necessarily in the interior of that, because it could be down here. It's in the interior of this big angle B, in the interior of angle B, such that angle CAD, is congruent to angle B. Okay.
Okay.
All right. From theorem that we proved over here, theorem 8.1, what do I know? If I have an angle here and I construct an angle here congruent to this angle, then the line that we get has to be parallel to this line. So from theorem 8.1, I know, why am I writing this weird? From theorem 8.1, I know line AD is parallel to L2. Going back to this proof, what did we do? We showed how to construct a parallel line. We said take an angle, and then construct an angle congruent to our given angle. And the resulting line is parallel to our given line. So I know that this line, AD, don't let my picture lie to you, I know that this line through AD is parallel to L2.
Right.
And it is in hyperbolic geometry.
Now, in our geometry now, we've now introduced our parallel postulate. So I know that L1 is parallel to L2, and I know that AD is parallel to L2. So what do I know?
That
LD lies on L1.
CAD.
That AD and L1 have to be the same line.
Right.
Because there's only one line through A parallel to this line.
Right.
Yes.
So we're using our postulate. So then from our last postulate, what is it?
8.1.
What postulate group are we on? Are we on postulate group 5?
I guess.
Yes, yeah,
Huh?
yeah,
I assume you're saying yes?
yes.
Okay. Then from 5.1, comma, AD and L2
We're on 6.
must be the same line since they both contain A. Seven. Therefore, D lies on L1.
It's 6. 6.1.
It is 6. Okay. So we're on postulate group 6.1. Thank you. So then we know that D lies on L1. So we know our picture in fact looks like this. And D is somewhere over here. Okay? What were we trying to argue? We were trying to argue that this angle is congruent to angle B. So therefore D lies on L1, which gives me that angle CAD, these right here, that angle CAD is congruent to angle B, which gives me that angle CAD's vertical angle is congruent to angle B. And there we go. We proved that alternate interior angles are congruent. So if the lines are parallel, then the alternate angles are congruent. Now the other direction is much easier.
Why did you go straight to 7?
Who knows? No idea.
Doing alright.
And the only thing I can think is I was looking at this and then went right. Okay. So now let's go the other direction. The other direction, we need to show that if our alternate interior angles are congruent, so if this angle is congruent to this angle, then the lines are parallel. So how do I argue that? So now, if I know that this angle is congruent to this angle, how do I know that this line is congruent to this line?
You know that angle A is congruent to its vertical. So the vertical of angle A is congruent to angle A. And you know that angle A, if angle A is congruent to angle B, which it is, then we know that they're congruent. I mean, they're parallel.
Perfect. So let angle A and angle B be alternate interior angles. The alternate interior angles such that angle A is congruent to angle B. So now we're talking about that is angle A, that is angle B. 7. Then angle A's vertical angle is congruent to angle B, which gives me that L1 is parallel to L2 by 8-1. Okay, there we go. Good?
Yes.
Now, this is true. If alternate interior angles are congruent, it would also have been true if we knew that, we won't bother proving any of these, but you can hopefully see how they're quick corollaries. Imagine instead I knew that alternate exterior angles were congruent. So imagine that I knew that this was congruent to this. Do the lines still have to be parallel?
Yeah.
Yes. Because if this is congruent to this, then this is congruent to this. And then using this theorem, those two lines can't ever intersect. So they're parallel.
And since A is congruent to B, then let's say that vertical angle is angle D, so angle D is congruent to A, right?
Yes. So, once you know a pair of corresponding angles are congruent, you're guaranteed that the two lines are parallel.
What is that angle called compared to that one?
If we do this one to this one, those are called alternate exterior angles.
Wait, what about that one to that one? So the top one, okay, that one to the top one.
That one?
Yeah.
Those are called corresponding angles.
Corresponding. Okay, right.
Bunch of terminology. But yeah, if you know corresponding angles are congruent, you know that the two lines are parallel. If you know alternate interior angles are congruent, you know the two lines are parallel. If you know alternate exterior angles are congruent, you know that the two lines are parallel. So, lots of ways of knowing that if you pretty much get any pair of angles to match up, you know the two lines are parallel.
And then 7, oh, you already erased it. But 7 and 3 would also be corresponding, right?
Yeah, I don't remember how I had it drawn. But if you look at definition 8.3 in your book, it lists out, it takes a picture and walks you through which ones are interior, which ones are exterior, which ones are corresponding, and all those relationships. Okay, so we proved theorem 8.4. Definition 8.4, what does it mean to add two angles together? How do I take the angle sum of two angles? So if I have this angle and I have this angle, how do I take their angle sum?
You put them together.
Yeah, you take that vertex, line it up with that vertex, and then you make one of the sides correspond with each other. So I take that, put it on there, exactly the way you were thinking, and now this whole angle we call the angle sum. And that's exactly what the angle sum is. We said two angles are complements of each other if their angle sum is a right angle. We said they're supplements of each other if their angle sum is a straight angle. Okay, so that definition works exactly how you expect. So did that. So now we're on to theorem 8.5. The angle sum of any triangle is 180 degrees. Let's prove that now. Or the angle sum of any triangle is a straight angle.
Right. That one, I'm right. That one.
So this is theorem definitions, theorem A5. Theorem A5. Alright, theorem A5. The angle sum of a triangle is a straight angle.
Yeah.
Or the way that we typically say that is the angle sum of any triangle is 180 degrees.
Yes.
Okay.
But we're not into measurements yet.
But we're not measuring.
Oh, yeah.
So it's a straight angle.
That's my question. When, since we're done with postulates, when do we start measurements?
Yeah, so we don't use a postulate, we don't use new postulates to talk about measurements. So we'll still talk about measurements, we just don't need to introduce any new
When do we
postulates to
start
do
talking
it.
about measurements?
I think that's chapter 10, but it could be 9. We're on 8. Okay.
Oh, yeah, this, question was on the test and you never taught it.
Yeah, sorry about that. Okay,
It was easy, it was going to put test.
let's go over the picture for this. Maybe we can just do the picture and don't need to write it out, I don't know.
Right.
We can write it out if you want. So we start out with some triangle ABC.
Such that triangle,
And then we construct the line L through point A such that L is parallel to AC. So those are parallel lines.
right, is that a parallel sign?
Yeah.
What line does AB, do you know, have to be?
So we start out with triangle ABC.
Okay, angle B
Extend
is
BC
congruent to
into a line.
angle A.
And now I know that there exists another line through angle A, or through point A, parallel to this line.
Right,
So I know that there exists some line L through point A such that it's parallel to line BC.
right, the interior of angle B. So which angle is B? Is B the outside of it?
This is angle B.
Okay, so B
This
is
is angle C.
congruent to angle
This is angle A.
LAB.
So since this line's parallel to this line, then I know, and we think about this line right here, AC as a transversal. So ignore this segment for a second. Pretend that this segment's not here.
Right.
Maybe draw in blue what we're paying attention to. So here I have a line intersecting two parallel lines.
Yes.
So I know that its alternate interior angles are congruent.
Yes.
So I know that this is congruent to this.
Well, that makes sense, so that proof was saying they just are congruent.
Now, think about our lines here, and think about just red as intersecting them.
We
So
know
now
that
red
C
is a
congruent to-
transversal on these two parallel lines.
We know that C is congruent to L.
Right, so angle C and this angle are alternate interior angles. So
They are congruent as well.
maybe we'll use blue here for angle C. So this angle, blue, is congruent to blue. So that's the same big as that. And then finally, this angle is the same big as itself.
Right, A is congruent to angle A, so
Right, so green, red, blue is the same big as green, red, blue.
it's the same size, yeah.
Same size. So this angle sum is the same as this angle
Sum of
sum,
green, red,
which
blue.
is a straight angle.
Straight.
What if you have a funky triangle?
So let's do it again, and this time let's get funky. So you start out by giving me any triangle you want. Doesn't matter what it looks like. So we'll get something weird looking this time. Something like this, right?
Yeah.
So I'm going to call this, doesn't matter which points I call A, B, and C. But I think it's weirdest if we call this point A. So trying to stick towards the weird case.
Okay.
And this is B, this is C. Step 1, extend out line BC. I know I can do that, right?
Right,
Step 2, construct a line through A parallel to this line.
right.
So I know that this is parallel to this. We'll call this line L.
So that's what, oh, I did not know.
And so angle B now is the same size as this angle because they're alternate interior angles when we think about this line as a transversal.
Right.
Here's a transversal intersecting these two parallel lines. Therefore, its alternate interior angles are congruent.
Right.
Similarly, this is a transversal for these two lines. And so relative to this line, its alternate interior angles are congruent.
Did you tell us the definition of a transversal line? What does transversal line mean?
It's just a line that intersects both of them. Sorry, it just cuts both of them. So I know that this angle is the same big as this angle.
So when we write this in a proof, we're gonna say let AC be a transversal line.
You're going to say,
Such that it
Alright.
cuts.
so we'll start right now. 1, let triangle ABC, comma, and let L through A such that L is parallel to BC. So that's how we started. 2, since AB, since line AB is a transversal, comma, its alternate interior angles are congruent, and that's how you say it. And then for 3, we say the same thing, but now rather than talk about AB, we talk about AC. So that gives me this, line 2 gives me that this is congruent to this. Line 3 would say the same thing, it would give me that this is congruent to this. And then finally, angle A is congruent to itself. And so once again, we get blue, red, green is equal to the sum of blue, red, green. Hopefully they're just quickly putting something up. All right.
So you were tapping the board really hard. I was like, jeez.
That's not how.
Yeah, I assume they're hanging something.
I thought you were pounding something. I thought you were pounding the board.
Like, jeez.
Not quite.
Passionate, yeah.
All right. Anyways, so there we go. That the angle sum of any triangle is a straight angle. Okay. Now with that, put a pin in it, and I'll show you a quick proof of the Pythagorean Theorem. Very pictorial one. I'm not going to write out the proof. We'll write out the proof when we get into chapter 9. But just pictorially, so you can see it and see that, oh yeah, that makes perfect sense. So here's a common picture to see it. Drawing out 2 triangles here. And we're going to think about this a lot like the Greeks thought about it. Over here, trying to mark off distances. All right, I'm trying to mark that off. Excuse me. So that this distance is the same big as this distance, is the same big as this distance, is the same big as this distance. Those are all meant to be congruent. You with me?
Yes.
So that red is supposed to be distance A, and the blue is supposed to be distance little b. So that's A, that's A, that's A. This is little b, this is little b, this is little b. Now, on this triangle, I'm going to do a similar picture. But for this one, I'm just going to mark off like this, like that, like this, and like this. Okay, so this is little a, little a, little a, little a. This is little b, little b, little b, little b. Now we use green to finish off our picture here. So in this picture, connect that to that, connect that to that, connect that to that, connect that to that. On this picture, connect that to that, connect that to that. And now, let's look at each of these. So first off, look at the entire square here. What is the area of this whole square?
AB squared.
A plus b squared.
A plus B squared.
So the area of this whole square is a plus b. That's our side length, squared. Similarly, what's the area of this whole square?
A A plus B squared.
A plus B squared. So they have the same area. Okay. Now let's look at the areas of each of these. What is the area of this piece right here?
A squared.
A squared. What's the area of this piece right here?
It's B squared.
A times B. Length times width. Area of a rectangle, length times width. So this is A times B. What's the area of this square?
B times
B
B
times
squared.
Oh,
B squared.
B squared, yeah.
What's the area of this square?
B times A.
A times B or B times A,
Or
but
A times A.
doesn't matter. Okay, so the area of the whole square is equal to A squared, plus we have an AB and an AB, so we have two ABs, plus B squared. This is how the Greeks would have proven that A plus B squared is equal to A squared plus 2AB plus B squared. You're used to doing an algebraic proof on how you expand that. Here's a geometric proof of it. This is how Euclid proved that.
Wait, parentheses, A plus B squared is the same as A squared plus 2AB plus B squared?
Yeah, this is a square. This is the area of a square with this as its side length. And that's the same as that square plus two of these rectangles. Identical areas. So it's a geometric proof of that algebraic property that you know and love. So that was just a side note. Similarly, over here, what do we get? Let's look at each of these. First off, what's the area of this square? Or of this triangle?
AB.
Isn't it half times?
Half the base times the height. So this is 1/2
A.
AB.
AB.
This is 1/2 AB, 1/2 AB, 1/2 AB.
Right.
Okay, now we're going to call this hypotenuse length C. You with me?
Yes.
Now, since this triangle is congruent to this triangle, since these are all right angles, that's a right angle, that's a right angle. So side angle, side, side angle, side. These two triangles are congruent. So this is also length C, and this is also length C, and this is also length C.
Because aren't all the triangles congruent?
Because all the triangles are congruent. So if I call this length C, then all those have to be the same length. Finally, one more thing we need to argue is that this right here is a right angle.
It is.
How do we know it's a right angle? That's where we use that the angle sum of any triangle is 180 degrees.
Yeah.
I know what's right.
So now I'm trying to argue that this inner shape is a square. The way I can do that is I need to argue that that angle right there is a right angle. Now, how do I know that that angle is a right angle? Let's look at this blue angle. This blue angle I'll call alpha. And the red angle over here I'll call beta. I know that alpha plus our mysterious angle here, we'll call it angle gamma. Alpha plus gamma. Let's do it all together. Alpha plus beta plus gamma. We know that this has to be a straight angle. We're just going to say 180 degrees since we're just thinking it through, right? Alpha plus gamma plus beta has to be 180 degrees, right?
Right.
Well, I also know since this triangle is congruent to this triangle, I know that this angle right here is also alpha. And I know that this angle right here is also beta.
Because all of the. These are all.
And so alpha plus beta plus a 90-degree angle
It's 180.
is 180. So I know alpha plus beta is equal to what? If alpha plus beta plus a right angle is 180 degrees, alpha plus beta has to be
90 degrees.
90 degrees.
If a right angle is 90 degrees.
Though
Right.
Alpha plus beta has to be a right angle.
Alpha plus beta has to be a right angle. Perfect. So now, I know alpha plus beta is 90 degrees. I know alpha plus beta plus gamma is 180 degrees. So substituting alpha plus beta is 90 degrees up here, I get 90 degrees plus gamma is 180 degrees. So substitute this into here. Alpha plus beta is the same thing as 90 degrees. So I get 90 degrees plus gamma is equal to 180 degrees. Subtract 90 degrees from both sides, and I get gamma is equal to 90 degrees. Okay, that's how we argue that this is in fact a right angle. So we know that's a right angle, and so this has to be a right angle, and this has to be a right angle, and this has to be a right angle. So that is in fact a square, and so what's the area of this C?
C squared.
C squared. Okay, so now let's add up our total areas. I got that the area of the entire square, this whole big square, is equal to, let's see, how many of these triangles do I have? 4. So I have 4 of those. So I have 4 times 1/2 AB, and then plus c squared. You with me?
Yes.
Now 4 times 1/2 is just 2. So this is the same thing as being equal to 2ab plus c squared. So I have a plus b squared is equal to this, and I have a plus b squared is equal to this. Or in other words, this has to be equal to this. So I get from that that 2ab plus c squared is equal to a squared plus 2ab plus b squared.
So
That's equal to that. Cancel out the 2ab's from both sides. I'm left with a squared plus b squared equals c squared.
So that's just two separate ways to solve the same thing.
So that is one proof of the Pythagorean theorem. And I did it very pictorially using things that you already have intuition for. We'll prove the Pythagorean theorem again in chapter 9.
Okay.
But, so there's an actual proof of it. The area of that square that we construct in here is exactly equal to the area of that square plus the area of that square. Because these two rectangles perfectly cancel out these 4 triangles.
Okay, yeah.
Yeah, pretty cool. Okay, so there's the Pythagorean theorem. Back to the book. We proved that the angle sum of any triangle is 180 degrees. I already jumped ahead, so then the book talks about polygonal paths, polygons, simple polygons, concave polygons. We already went over that last time. So I already went through all those definitions with you. Sorry, not concave, convex polygons. What was a simple polygon? Let's remind ourselves. Simple polygon.
Oh, semi-polygon, that's,
It's a
Is this a simple polygon?
Isn't
no,
it?
it's not.
Yes.
It is?
That's simple. Let me give you a polygon that's not simple.
Oh, yeah.
Oh, that's
ones
right.
that don't touch.
That's right.
So,
Polygons don't.
It doesn't
don't
intersect on itself somehow.
Intersect.
Right, don't
All right.
intersect.
But this one was not convex. Here, let me give you a polygon that's simple and convex. Simple and convex. This one is simple but not convex. What does it mean to be convex? It means pick any 2 points on the polygon, draw a line segment connecting them. It doesn't intersect any of the sides.
Right.
That one does, so this one's not convex. Over here, if you pick any 2 points that aren't on the same side of the polygon, pick a point there, draw a line segment between them, it will never intersect any of the other sides. That's what it meant to be convex. Now, we're going to notice some cool things about simple convex polygons, using the fact that we know that the angle sum of any triangle is 180 degrees. So, let's start thinking about simple convex polygons, and I'm going to start, we're going to think about their angle sum relative to how many sides they have. So I'm going to use
convex polygon is
and then we'll have angle sum.
Is this part of chapter 8?
Yeah.
chapter.
Chapter 8.
So we're going to think about simple convex polygons of n sides, and we're going to think about their angle sum. Now we already proved that if it's a 3-sided polygon, it's a triangle, then its angle sum is
180.
180, or one straight angle. I'm going to do 1s, s for straight angle.
Okay.
2s for 2 straight angles, 3s for 3 straight angles. We'll count it in terms of straight angles. With me?
Yeah.
Now let's think about any 4-sided figure now. So pick any 4-sided figure you want.
The squares, 2s.
Well, we want to do any 4-sided figure, as long as it's simple and convex. Now let's think about its angle sum. What's its angle sum going to be?
2s.
How do you know?
Well, it's not.
100%. Because
He's right.
Yeah, I think so.
it is bad.
How do you know?
Because it creates 2-sided angles.
Because what?
It creates 2 3-sided angles when cut in half.
It creates 2 3-sided angles when cut in half.
Well,
I think you have the right idea, you're just saying it funny. It creates 2 triangles.
creates 2
If I slice that, now we have 2 triangles. Add up all the angles. This angle plus this angle plus this angle, that's one straight angle. Plus this angle plus this angle plus this angle, that's another straight angle. And so if I add up that whole thing, plus that whole thing, plus that whole thing, plus that whole thing, I get exactly 2 straight angles.
Okay.
Alright, what about any 5-sided figure?
3.
So if I've got any simple 5-sided convex polygon, what is its angle sum going to be?
3. He's right.
3 straight angles?
You can make it into 3 triangles.
Exactly, you can split this into 3 triangles. And so it's going to be, if we have 5 sides, it's going to be 3s. And if we have 6, then you'd be able to split into 4 triangles, 4s. And so in general, if you have an n-sided polygon, what's its angle sum going to be?
1 less than
N minus 2 times s, where s is 180 degrees.
Okay.
Make sense?
Yeah.
So if we have a 12-sided polygon, what's its angle sum?
12.
10.
10s. Or in other words, in terms of degrees, it'd be 1,800 degrees
Would
if
a
you
circle-
added up all its angles.
Would a circle be a polygon?
No. We will think, we'll come
It's
to it.
infinitely
We'll
sided.
come to a way of thinking about a circle as an infinite polygon.
Infinitely sided.
Kind of. We'll have to do some hand waving and introduce you to the notion of a limit.
Of what?
So
Of a limit. It's a calculus
angle
concept.
sum of that is. Let me think.
It's going to be 3 straight angles. Because there's 3 triangles.
That's 360 degrees.
No, 3 straight angles.
Yeah, you're right.
That's 5.
180 3 times.
5 minus. Oh, 2. My bad.
So you're doing 3 times 18.
Oh, yeah.
Or 6 times 9 is probably an easier way for you to see it.
Okay.
56. 560.
560.
You got it.
It's 560.
560. Try again.
54.
54. 9 times 6 is 54. Add the 0.
Yeah.
You don't need a calculator for that. You're doing 18 times whatever number here. If we're doing 18 times 4, that's the same thing as 9 times 8. You can easily do that in your head. 72 or 720 degrees. But that's for angles which we're not interested in. Okay, let's ask a second question now. Let's look at the sum of their exterior angles. So that's the angle sum. Here we're going to do exterior angle sum. And what do you think is going to happen here? Any guesses? Let's try it with the triangle first and then go from there. Alright, so thinking about the triangle, let's add up all its exterior angles. So here's one exterior angle. Here's 2 exterior angles. Here's 3 exterior angles. So we're going to add all those up. That plus that plus that. And what are we going to get?
180 degrees.
180?
360.
Well, let's think about it. If we added up all the red, so if I added up this, this, and this, what would I get?
Oh, you get 540.
The red would give me 3 straight angles, right?
Right.
Now I minus the interior, I minus 1 straight angle, which gives me 2 straight angles. So all the blue would add up to 2 straight angles.
Okay.
With me?
Yeah.
Okay, now what do you think is going to happen if we do a 4-sided figure?
3s.
Then we're going to get 3 straight angles, right? So obvious we don't even need the picture.
Yeah.
No.
Okay, let's do the picture anyways. Just for the fun of it. Okay, so let's look at its exterior angles. So here's 1 exterior angle. Here's 2 exterior angles. Here's 3 exterior angles. Here's 4 exterior angles, right?
Right.
Now once again, if we add up all the whole things,
That'd be 4s.
then we get a total of 4 straight angles. But now we need to subtract away how many?
2.
2 straight angles.
So it's
And we're left with
2.
2 straight angles.
So it's 2s always.
So it's 2s always. It turns out it's always 2s. It's going to be the number of sides minus the interior leaves you the exterior.
It's always 2s.
Yeah, so it's always going to be 2s because our general formula for how we calculate this every time is we take n and then we minus our angle sum, our interior angle sum. The number of sides is how many straight angles we're adding up. So when we had a triangle, we were adding up 3 straight angles. Then we subtract the interior, leaves us the exterior. If it's 4-sided, then we have 4 straight angles that we add up, and then we subtract away the interior, and that leaves us with all the exteriors. So in general, it's n minus the interior, but we already found out the interior is this. So it's n minus 2 all times s. Distribute the negative through, and we get n minus n plus 2. That's the same thing as just 2. So it's always just 2. Amazing. Any simple convex polygon you draw, if we add up its exterior angles, it will be exactly 2 straight angles every time, no matter the polygon. Amazing. Right?
That is.
Okay. That is the last thing that we go over here. All he goes over after that are some definitions that we already went over last time. Parallelogram, rectangle, square, rhombus. I just did all those in one go because we had to talk about polygons twice. So I covered everything else he talks about last time. Any other questions you have that you wanted recorded? This will be the end of chapter 8, and this pretty much ends the first half of the book.
So 6.
And we're now finished with
Postulates.
all our postulates. Is there 16 chapters? I don't know, because we skipped the introduction. But yeah, it turns out there is exactly 16 chapters.
Skip the introduction and we skipped
We just skipped the introduction. That's all we skipped.
chapter 1.
That's the introduction. All right, so no other
Philosophy of mathematics.
no other questions?
It's gonna be fun.
Okay. It's not going to be as fun as you think.